Very good morning to all of you, Putala. Today, 4th February, the Independence Day, somehow. Lesson 5, Thermodynamics. So we welcome all manufacturing mechatronics and BST batches, 2 or B1, semester 2 for today lesson. Putala, ඇහෙනවද කියන එක?
Yes, sir.
ඇහෙනවද පුතා?
Yes, sir.
Okay, very good. Very good. Today, this is what the plan is. I just put here as insight to SFEE. Later we will know what this is. And also moisture in air. Moisture in air, understanding of moisture in air is very important. Of course, for BST, they are dealing with some comfort, cooling and air conditioning solutions under building service technology. So you are very basic. Learning start from moisture in air when it comes to air conditioning. So that is very important for manufacturing and mechatronics as well. So there are a lot of solutions, applications, products, and even designs related to this moisture in air aspect. So we have to understand this very well with some scientific base so that we will be stronger. Yeah. So in short, if we learn this subject very well, when we deal with the applications, we have a very good confident level, high level of confidence. If not, it is something like a blind approach. So we will see how we can learn out of this. So even today lessons, we are not doing anything about maths, but try to understand the phenomena, concepts, and the thermodynamics models. And later we will do some maths evaluations whenever it is necessary only. Yeah? So you should believe that thermodynamics is not maths. That's true. You have to have a very important understanding. So if we look into the last week, lesson 4, we came out this slide as the final one. So we learned a lot here out of this learning. We learn about enthalpies, maybe better. If we can look into lesson 4, maybe a little bit to get some refresh on the subject. Lesson 4. The lesson 4, flow work and displacing its environment. So we learn about this. You better go through the notes and all. So, and we learn about the flow works as well as the enthalpies, enthalpy definitions, and also we learn about internal energy. And also, other than the enthalpy and internal energy, we look into this turbine engine. Okay. So lesson 4, we ended up with this understanding. So today, yeah, we have done a lot on the cycle as well. The 4 processes you can see: the compression, intake and compression, combustion, and the turbine section is really delivered the power. So that's the power section, turbine and exhaust. So something like intake or suction, compression, combustion takes place, then you have the power, then you have this exhaust. Suction, compression, plus combustion, then your power and exhaust. So you can say it. So again, we came to this, so we are going to discuss this afterwards. So this is the last week approach, and this happened to be the final slide. So we will start from here today. I will take section by section here. So first I will take the intake and compression. So the compression, there are sets of radially constructed set of blades here. So turning makes the air comes in and then squeeze the air before going into combustion chamber. So you can see intake as 1 and compression, end of the compression as 2. So if you model this, it is something like squeezing, reducing the volume. Okay. It is something like reducing the volume, and we have learning that. Previous lessons. Even the shape here you can see. Something like almost like this, reducing the volume, squeezing. So in reducing the volume, let me So there are a set of blades. There are a set of blades. And this the model. So you have incoming air. Incoming air, I just put in this way. In. Okay. Yeah. Actually, it's a single line in the real modeling. It's a single line. So air in. Air is the working fluid. And it leaves here out. Okay. And other than that, there is a work done on the system, because the work done means the turbine blades are being turned with some considerable power, because squeezing air is not that easy. If you see bicycle pump, if you pump, if it's a hand pump, bicycle pump, so if you pump air, so you see how difficult it when the pressure is building up in the bicycle tire. So you see it needs a huge power when it's come for squeezing in bigger ratios, squeezing in bigger ratios. So I'm drawing the shaft here. Shaft this way. Shaft. So shaft work, he input shaft work here, means turning. So there should be, inside there should be a set of blades. So that mechanical component, if I need to draw, still I can. Connects to the shaft. Give me a second. Never mind, it's okay. So the middle part here, you can see the shaft and the set of blades here. So the input work, it's a torque. Okay, it's a torque. Like this, shaft power. So let's see, the input is W. W. Input is W. And the air comes in and air goes out. In this case, comes in and leave. So in and out. So this H1 and H2 you can see here. So I can mark the same H1 and H2 here. So in the model, you can have same line H1 and H2 and W. Okay. So even you can, in this picture, if you need to show W, the work done, still possible. You put an arrow here, make it more visible. So color, I will put a color to see here. So input work, I think better. I will use this way. W. That's better. Input work. Okay, good. W. It's the same. Okay, now see. Here I mentioned about the energy balance. For this case, energy balance. So we are adding this W to energize. The air comes into the compression and we make it energized by compressing. So compression makes the air or the working fluid energized and leave it here at 2. So energy balance for this compression processes, as I mentioned here, H2 minus H1. So the compression work is H2 minus H1. W, and you can see this W is H2 minus H1. W is H2 minus H1. So W, H2, H1 all have the same unit. So if you talk about the unit, you can have this in kilowatts, okay, or even kilojoules per kilogram, or even you can have kilowatts per kg. Later we will see units, possible units, okay. So it is interesting. So hope you can understand this, but there are many more things to learn. For this case, for the compression part, you can write it in this way. Okay. Later we will have a complete knowledge on this. Don't worry. Then we will be looking into the other component, same way. Combustion. See, combustion part. This part, combustion chamber. The combustion chamber. Now, combustion chamber is like this. So the fuel line comes in, you can see the fuel line here. And combustion adds energy here. So still working fluid passes through this. So here, so what we will do is, no W. Okay, there is no W. Combustion chamber in is H2. Previous one. Here it is H1, right? So combustion chamber inlet is H2, leaving is H3. But keep in mind, inside there are no mechanical moving parts. And there is no shaft work or work done, all out. And this shape is mainly the standard for the compression. So we will take this shape different. Okay, there should be some pressure rise, and there may be a slight increase of volume as well. There will be increase in volume a little bit, but not, there is no any expansion. So you have H2 in and H3 out. So in and out. So I will change the flow in and out like this. H2 and H3. H2 also. No more W. This becomes Q because of the combustion. Because fuel comes in and the air comes in, combustion, and the highly intensified energy addition is there. Addition. Yes. So highly intensified. I think better put more red color. This is the combustion chamber. Like this. So energy input here. Okay. So when you're following this, you will receive a good knowledge really. Now energy balance. Combustion. Combustion makes the energy level rise. So we are writing this as the increasing in entropy. H3 minus H2 means the entropy increase during combustion. So W we should replace with Q. Maybe small q. H3 minus H2. Why? The units are the same. Kilowatt, kilojoule per kilogram, or kilowatt per kilogram. So let's say, later we will talk about the units. Okay. But when it comes to enthalpies, generally we consider kilojoule or kilojoule per kilogram. I just put this. Okay, not to get you misled. And what is H? What is H? So you must have some upfront sense of H. We have discussed about H in lesson 4 a lot. The H contains the internal energy plus the flow work, or the work needed to displacing its environment to occupy the space. So H you should know. You should try to understand more about this. So we have discussed. So H is internal energy plus the work necessary to flow in and flow out. So H is U plus PV. So you have an upfront understanding of this. That is very important. Okay. So if you have no upfront understanding of H, you have issues of imagining this. So things, the flow comes in, move out. So move out, you have to displace whatever upfront. Goes in, you have to displace whatever upfront. So there is a flow work. To flow in, there is a work needed. Flow out, there is a work needed. So there is, other than the internal energy, you have PV component as well. So here for H2, you have this U plus PV at 2. H1, you have U plus PV at 1. Because we talk about energy balance. Okay. Energy balance. So U is the primary, the energy content in this working flow. Okay. But the flow work also involved here, because this also, by means of having PV, this has a higher energy level. Okay. Additional energizing to push through this. So H2 is something like a total energy, including the energy or the energized because of the flow work. Okay, because this energy is needed to push this in and push this out. So additional energy need for the flow work is also included here. That's why here as well, H1 and H2. So it is very important for you to go through your notes in advance. Okay. your notes in advance is very important. Because otherwise you will lose your understanding, the level of understanding. And also you have to have some sort of familiarity of this. So it is very important to revisit your notes. And even I'm putting the video of the lecture. It is very important. And also your one-time note, you should read it. It also explain it in a different way in your one-time note. So this is supplementary, okay? So finally, Q is H3 minus H2. Because learning, the sharing of knowledge, both parties must be cooperative, okay? You have a big responsibility in learning this, okay? Good. So even if we visit our one-time note, see, this note is with you. The flow or displacement energy. So that's how it's mentioned. So I talk it as flow over. So flow or displacement of it. So in a text, so this is explained here. So you have to go through this, okay? And you have to understand the daily notes, and you have to get the doubts also clear. Okay? It is very important because this has practical applications, practical interest are there. See, heat received or rejected. So quite related to combustion chamber. External work done. The compression, you talk about this external work done. That's why it is very important. Always look into your part here as understanding your one-time note. Okay, because understanding is totally your responsibility. So back to the slides. Maybe I will go for a slide. I'm not going to discuss the one-time note. So you should go through, but I will show you how these are connected. You should go through this. Okay. And see. Under these topics, that's why you should go through. Don't wait for the class to remind this to you, right? External work done. External work done. See here, I have a direct relevance unit. External work done. It's W. So you should have a bit understanding. So whatever I'm sharing here related to your notes as well. And the heat received or rejected. In this case here, heat received. In this case, it's about heat received. So that's why. So finally, you have this. Q. I will put small q. Even we have big H and also big Qs, don't worry. Anyway, I just put here, no issues. So you should understand this. Huh? So this is a very worthy subject, worthy to learn. So you should read those. Then we will go for the third component, power. Today very good that no one's in the attendance. Huh? So the last 30 minutes we will do that. Get this. Turbine. See turbine. It's turbine. Turbine. So now H3, because energy comes in, because always with the flow energy, other than the enthalpy, sorry, other than the internal energy, there is a PV component. Okay, there is a PV component. Means the flow or displacement energy component. There is a flow or displacement energy component. Always. See. So even about the internal energy, in your note, look into note. This is about internal energy. So you will see there should be discussions about enthalpy as well. And so it is very important to understand this. So going through the notes really helps you. Okay, good. So back to the combustion process. Okay. Sorry, not the combustion, the turbine process. So here, the turbine, it is related to external or internal work done. So here, external work done. Okay. So all relevancies you will see. So in our previous note, now this is not about combustion. I disturbed this slide. So I should come here for that. External work done. Here is the turbine. Here it is the combustion. So external work done. W. So W is the relevancy now. W. But now we have to replace this with turbine. Let me try this way. I'll draw this. So turbine, see the shape here. Can you see the shape? Because this working fluid expands. Expands. Working fluid expands. And in this expansion, of course, you can see the blades here. The rotating radially fixed blades. Okay. So that mechanical part, because when the working fluid expands and moves some mechanical parts, that produces work. So same like here, but in the opposite ways. Let me do this way. The blade is little smaller than this space, because this space accommodates the working fluid as well as the mechanical components. So, exactly like this. Turbine blades. Plus the space together, the produces this power. Yes. Now work done. So you should be able to construct this nature of schematics. Very important. Okay. Work done. What is work done? W. See, W here, same like the compression. If you know compression, you know expansion. H1 and H2. Now you have the H1. So I believe you should be understanding something very good here. H2 is here. Put this way. That is a kind of standard. So we call this construction in this way a physical model of this process, the turbine process. The expansion takes place. This is the physical model. So H2. H1. U plus PV. 1. H2 is this. This is now external work done. Interesting. Of course, H is U plus PV. You should know this. Understanding of enthalpy is very important. Actually, in the real understanding of enthalpy, sometimes even very difficult to explain, but internally, your understanding is very important. Enthalpy is something like this. And try to explain in your wordings. Now not H1 and H2, that is H3 and H4. So sometimes I may do mistakes, but you have to remind me if there is a mistake. Right. Very nice. External work. See, from your notes. So notes belongs to you, not to me. Even though I pass it to you. Very nice. Now, come to the energy balance. No more combustion. So, back here to power out. Power. So this is what external work done. So we have to rewrite W H4 minus H3. Actually, if W this direction, you can see this H4 is lesser amount of energy because part is done here. So I will put this way, okay, instead of W, I will write this way. Originally you have H3, but out of H3 some work is done. And finally, what remains is H4. Interesting. So in this case, you can write W again. If you really need. W is H3 minus H4. It's W. H3 minus H4. Is W. So even you can write negative W as you take negative W, means you consider a negative W, then that is H3 minus H4. Okay. Later you will see why I put negative W. You can think about this. Afterward, same. H3 minus H4. Yes. Okay. So this is basically the energy balance. So you should understand this. Look into the one time mark. So you have to learn some more here. But basically for turbine, you can see this. Okay. So this knowledge will be very useful. So later we will revisit the same expressions. Okay. We will revisit the same expressions. So intake and compression, combustion, expansion, and exhaust we will talk later. Exhaust component. We will talk later. There is a reason even here I did not mention about the exhaust. So that is later discussion. Because this has a nozzle, you know. So this is different. Why different? Exhaust. Seems like a nozzle. See, the cross-section radius. So this has something like the effect on the rockets, the propulsions. Okay. So you can see this. The nozzle effect is there. So we cannot simply write this. And one more, I will add here. in your wording, heat received or rejected. Let's say sometimes for these cases, there is a possibility. There is a possibility to leak heat as well, because this is quite hot and outside may be cold. So you have some heat rejection is possible. Let's say. Yes. Heat rejection. Heat rejection. Maybe a new slide. Heat rejection. So it's something like a heat loss. Okay. Heat loss. Heat rejection. Heat loss possible. Heat received or rejected. I think this a bit. This will be. So let's say this heat rejection is Q. Heat rejection. So Q. Heat loss. Now, Q rejected. If not rejected, this helps for the work done. But now, Q is rejected. Minus Q. So W plus Q. So it's minus Q. So You have to take the Q into consideration. So losing of heat from the surface here. There is a loss as well. So you add this Q also into this. Because initially you have energy level of H3. So this working fluid contributes for work W amount, different W now. And also this Q loss is from the working fluid. That is from the working fluid. The source of this heat loss is the working fluid energy levels. So H3 minus W minus Q. You have to take all release from H3, results H4. Writing in this way may be better. Put some brackets. Okay, good. See. Interesting. This seems like a nozzle. Okay. This seems like a nozzle. So flow through a nozzle section. Actually, you have to understand this. So, attention, very important. Your effort to understand this also very important. Okay. So your imaginations very important. You may have Q here from the surface. Also, you may have Q component. Yes. But you may have, you may not have. And the point is, when it comes to energy balance, so you must have a good understanding about energy types. Okay, energy types involved here. So you can see one energy component, of course, related to internal energy plus flow work. So are there other components? So you know U plus PV, you know this. Please don't send the attendance now. Right? You have enough time, Madhushankar. Still you have time. U plus PV. This all takes together because within this PV is there within this working fluid. And another component related to, have you heard of kinetic energy? This is the energy due to velocity. The bulk motion of the fluid. Okay. Bulk velocities. Okay. Then because of the velocity, there is a kinetic energy. And also, there is another component. You should learn potential energy. So here, potential means gravitational potential. It's coming down because there is an energy component, potential, the stored energy there, potential. Okay, potential energy. So there are other components as well, other than this U plus PV. So when the flow from the combustion chamber comes here, comes from everywhere, surrounding. This is coming. So I will just put just one more. And leaves here. Okay, comes and leaves. So it's something like a nozzle. This part, only this part. So if I take that nozzle, you feel it is something like a compression shape. See, a reduction is there. But the point is, inside, no moving parts. That's the point. Compression, same way, but you have the moving part. The moving part is there. Here you have the moving part. Even turbine, you have the moving part. But here, no moving part. So inside, consider empty. It's a space only. But externally, there is a frame or casing like this. Exactly this, exactly this you can see. Still active here. So this is how you are modeling. Coming from the combustion chamber, energized flow, and leaving it. model. Exactly, you see the shape. So now 4 and 5 sections. Here velocities are very high velocities because this can push forward the aircraft because of this thrust, because of the higher velocity. Okay, higher velocity. So the velocity related energy level is very important. Even incoming also. Certain velocity here, leaving is a very high velocity because of this. So the kinetic energy component is sizable. But in turbines, you may not be considering this. In the compressors, you may not be considering because the other energy level, other types of energy, the enthalpy is the highest. Compared to enthalpy, kinetic energy levels negligible. But here, it's a very high speed. So now the kinetic energy will come into play. So your kinetic energy here. I just put KE, kinetic energy. So here it is 5 maybe. Key 5. Because section 5. So also you have to look into, if you take kinetic energy one side, section 4 also you have to use. So yes, other than K, just put simple letters, maybe small letters. K. K. Other than that, you have H. H4 here. K4. So here we are moving forward with this energy balance understanding with some practical mindset, you know. For K4. So other than that, you have loss possible. Yes. But no work done because inside no moving parts. So W is exactly 0 on thermodynamic point of view, let's say. Because working fluid flow through and it won't turn any moving part. W is 0. So you should notice this. There is a possibility for Q. There is a definite situation where W is 0. You may have a value. And kinetic energy is energy due to velocities. Okay. The working fluid velocities. So it's moving like in the packets, in the bulk phase. Okay. one packet after the other, something like that. So kinetic energies and the enthalpy. Because the flow comes out, must takes over the surrounding. So that's why other than the internal energy, PV, the flow work effect is there. Even upfront, to replace this, flow work energy potential should be there. Energy is there, energized with this, energize this incoming working fluid, the H4, U plus PV component also. Then the gravitational potential. So you have to have, let's say, the gravitational potential, you can think in this way. Of course, above the ground, how high? You have a potential. We'll take this way, gravitational potential. Let's say, I will let you imagine this a different way. Okay. Imagine a coconut. Coconut. So I draw it. A coconut size flow component. Already size of it. Coconut size flow component. Yeah. I will imagine this. Olga Pusate. But leaving also the same here, let's say the mass equivalent here. Leaving. So it won't comes down here. When it passing through here, there is no chance. So this same mass. It follows the same line. So if this is the ground, this is for your imagination. Okay. So this is not dropping. It flows through here. In a fraction of a second, it's very fast moving through here. So the height above ground level of this, imagine coconut-like working fluid parcel. This is the height. I will make the height in a different way. Yes, at this height. No height change. You cannot see that. No height change, even during the leaving. No height change. Let me change the color to brown to connect it to the ground. Yes. Q. Are you sending the attendance? Later, Bhuta, yeah. See, you are asking the questions. Very good. So, same height, imagine a coconut-like parcels of fluid flow. So, your gravitational potential energy, you know, this is mgh mass times the gravitational acceleration times the height, mgh. So, if you have little m here, because I'm explaining this because everything will be cleared for you. So, no height change because immediately passing here. So, mgh has no change. Same h. Let's say this is cruising or flying. So anyway, this takes no time passing through this nozzle compartment. So whatever the height, it's the same for this. Passing through the nozzle H. So all mgh same. So you can see that gravitational potential energy mgh, no change. Even on the ground turbine, even flying, no changing of this. Imagine that coconut-like parcels. Okay. Yes, good. This is a coconut. Same height. interesting. See, so no change. You imagine the same like equivalent mass is flowing. So it's very interesting. Now you can see the gravitational potential energy, no change. So initial, let's say, go to another slide. So here I change this H2Z just because of one reason. H we are using for enthalpy. Okay. So now you H height is no more using H instead of mgz. Okay, mgz. So I extend this. So I'm coming. Yeah. Z. Leaving Z. Z. But for this case, 4 and 5. So after this, I will give you a break to time. 4 and 5. Four, 5. H5. This is H5. K5. Take this out. Okay. It's okay. So H4, K4. Quite compact slide. But understanding is very important. Small, hopefully you can see this. Let me make it a little bigger. Yes. W is 0. I put it here. You know why W is 0 now. Well, those are very important knowledge. Because no moving components here inside, driven or moved by the working fluid. So enthalpy, kinetic energy, and also the potential energy. Potential energy, it's a PE. PE, just use P. So all the types of energies. But here it is P4. See, because of the nozzle components. So how the situation changed. Interesting. So P5. So for this nozzle, here is a possibility. Let's say we slide. Let's say we take Q out. We'll keep it. So then energy balance. Make this a little smaller. Just to show our memories on previous thoughts. Now we are ready to write the energy balance. What? You can write now. Originally, you have this. Finally, you have this. Okay. With the original one. The original energy level. Lost some heat. Q. Some heat. Yeah. Original energy level plus some heat from the surface to ambient. As a result, final energy level is this. Okay. For convenience, I take the coconut out. So initial energy level, final energy level. Your Q is out. Q. Z remains the same. Same. Interesting. So this is your equation. Energy balance. Okay, good. Now we will see what are these. PE4, you know that PE4 is Mg is Z4. PE4 Mg Z4. P5 MgZ5. Yes. Interesting. H4, you know. Fine. You have understand. So P5, you have Mg set 5. Good. K4, say the coconut. M, coconut mass equivalent flow. So what's the velocity here? Let's say V4. So then your K4 is interesting. No. K4. Half mv squared. Half times mass times velocity to the power big V. Yeah? See the importance of imagining this coconut equivalent. And if m is 1, later, half mv squared. K5 half mv squared at 5. E5 mg H5. So H5, if H is for 1 kg, small h for 1 kg, then m times H5 is for m kg. Just imagine. M times H4 for m kg. Small h is for 1 kg. Little congested. Don't worry. Yes. Good. This is how the energy balance now. This is how the energy balance. So interesting. Good. It's really good. See, you have the nozzle. You have noticed how we get this shape. So masses moving here. Parcels like working fluid or the gas. Of course, it's fully filled, but imagine M parcels, many flow. So potential energy, gravitational potential, MEZ, MGZ. Kinetic energy, half mv square. The new one to you is enthalpy. You already know it. Quite interesting. Yes. Good. Then we are going to develop. Because see, the same mass, so we consider the same mass flow rates. Flow rates, whatever goes in, equivalent should go out. So we call this the steady flow nature. If M goes in, M goes out. So what remains here is the same. So this is something like a steady flow nature. Steady flow. SF, steady flow. So energy balance is energy. We call it equation, SFEE. Steady flow energy equation, that's what? Insight to SFEE here. But our approach is different, okay? So we are learning with some practical applications. So that is the specialty of our approach. So insight to SFEE, that's all. Later we will simplify this case by case. So afterward, so we will take a break, Putana. And I need a break. 10:38. Kid Humbrain. 10:50. 12 minutes at the. Okay. 12 minutes at the. Abuta. Manusha. 12 minutes enough. Okay. Maybe 10:45 we will meet then. Okay. Since no response. So we will meet at 10:45.
So 1050 or what?
1050. Okay, 1050 then. Okay, 1050, and we have very interesting topic. Evaporative, yes, moisture in air. So we have to study that as well. So this SFE about to complete. So we will look into that. The remaining 1 or 2 slides we have to develop up to 1050. So see you at 1050. Okay. Right.